Cool. All right. Here we go. Welcome everybody to another Neo4j live session. This one a little bit different. When we were talking a little bit about this earlier this week or end of last week, Olga and Stu, you said, well, this might be new for me as well, and I'm pretty sure it is. So I'm very excited to have you two join us today, where we talk a little bit about network intrusion detection, everything done on Snowflake, if I'm correct, and this mix between running graph algorithms on Snowflake is a pretty cool new addition, new feature that has been recently made possible or made available. So it's very exciting to me. It's all very new. Stu and Olga, both you have written an amazing blog post earlier this year in April, which was then, I think this was kicking this all off. I was seeing it, I was reading, I was thinking, oh, this is interesting. Obviously, Michael read it, and Michael said, well, you need to talk to Olga and Stu about this, and you need to have them in the stream. I said, that's okay, let's do this. And so greetings to Michael if you're watching this. This is all how it kicked off. So I'm super happy to have you two join me today on this nice summer day, at least here in Munich. Welcome Olga, welcome Stu, and nice to have you on the show.
Excellent. Thanks, Alexander. Thanks for getting us on the show. Yeah, it's great here, just outside London as well. Yeah, I'm Stu Moore, product manager for our graph algorithms on Snowflake. I cover some of our data ecosystem products as well, like our Spark connector, and Databricks connector, and some of the other ways of getting data in and out of Neo4j. But one of the most exciting products I've worked with and built with engineering, my time at Neo4j, is definitely graph algorithms for Snowflake. Our ability to, as you say, run all those great GDS algorithms on data right inside of Snowflake. And one of the recent features we launched not long ago was the Python runtime. So algorithm like GraphSAGE can now be run on Snowflake's GPUs. So super exciting, super powerful stuff. But one of the things we always have kind of problems with for people trialing our product, because we give a 30-day trial, is they don't always have good data sets available, and that was one of the motivations behind the blog. So I asked kind of Olga, hey, can you go out there, find an interesting data set that would work for GraphSAGE? We can show off our capabilities on GPU. And over to you, Olga.
Yeah. Thanks. I'm Olga Razvenska. I'm a member of Graph Data Science team at Neo4j, and yeah, when I got this request, I was I was really engaged, and I was really happy to having this opportunity to find something new, something that is not about flights connection or something like that. So when I found that paper that we will that we reproduced, and we will show the demo and some further steps today about that. When I found that paper, I was really happy because it's something new. This is Dataset, and actually we get in touch with researchers and with people who is in charge of this dataset. They allowed us to use it and to show our capabilities on that data. And I was really happy that our application on Snowflake can cover the whole paper with just 3 calls to the application. So yeah, I was really excited about that. So that's why we've got our blog post. So yeah, happy to demo it today.
Very cool. And the paper, because we mentioned it a couple of times and people might not have read it. So the paper is talking about network intrusion, network, I guess, resilience at some point, or loopholes in network protection
Yeah, that's right, Alexander. They basically kind of formulated this kind of hypothesis that there was a better way of spotting intrusion attacks on, particularly focused on the IoT device network, because there's such a wide range of devices, protocols, and obviously, attackers, hackers looking to exploit lots of different types of network. You've got the rise of AI, which makes it super easy. No one has to go to the dark web, unfortunately, to get hacking tools now. So what they found was, just traditional tables were not the best way of analyzing the data. And even graph, if you construct a graph of how devices are connected to each other, that doesn't really help solve the problem either. So they came up with this approach, which we'll talk more about in a bit. But I think it's a great application of a technology to be able to spot malicious attacks on your network and differentiate them from just benign network connections. So I want to pay a big thanks really to the work from Victoria University and the Dataset from the University of Queensland. It's been pretty helpful.
Super, and we couldn't have timed this any better, which we obviously we didn't know, but today, I think it was today or tonight, I don't know. But when when OpenAI announced that their AI agent was hacking a Hugging Face by accident, I think this is one of the reasons where you should definitely pay attention to what Olga and Stu are going to tell you today, and think about, is there something you can do to prevent these kind of things when everybody's building hack agents?
Of course, our demo won't cover this.
No, of course not. No.
I think you can get some food for your thoughts and get some inspiration on, we will show at least 2 ways for graph construction from the tabular data, and I think that can inspire people on the stream to look at their problem from the different angle.
Yeah, cool. That's great. So I think before we dive in, I think Stu, you've got a little bit of a presentation to give us a bit of a overview, I guess. But I don't know. Do you wanna share a little bit about the work that went into the blog?
Yeah, sure.
Before we do that, or is there like a good intro before the demo?
Yeah. So I kind of really set the scene on really explain how our product works. Obviously, most people maybe in the audience are familiar with Neo4j, the graph database. We got fast traversals. You've got Cypher. Inside of Snowflake, you don't get the core database. You get the graph algorithms and a way of taking your tabular data and constructing a graph. So I'll talk a bit about that. I will touch on and explain briefly how KNN and GraphSAGE work. I will do my best here. I'm not a data scientist, so later on you might find Olga corrects a few points that I make, or maybe just clarifies a few things. But she will put the algorithms in the context of how we are solving the particular problems and running through. As I said, I wanted to say a big thanks to the team at the Institute of Sustainable Industries at Victoria University, Tengno, Jiao Yin, Yongfei Ji, and Hu Wang. They wrote a paper optimizing IoT intrusion detection graph neural network approach with attribute-based graph construction, which basically means we're going to solve this with GraphSAGE and KNN. There's also a big thanks. We couldn't have obviously done this either without the data, which is publicly available from Mohammed and Sumac and Marius from the University of Queensland, Australia. And apologies for mispronouncing any names there. So why graph and graph machine learning? Well, we're looking at similarity, right? The way KNN works is that it finds the top K, or in our case, we use 9, top 9 most similar events, and then it constructs a graph by creating a set of relationships. So we're taking data that represents the connections that occur on the network. We're not saying this connection is connected to this connection. We are saying this connection event is similar to this connection event. And if we meet certain criteria, then we'll construct a graph on that. And then we'll take that graph and we'll pass it into GraphSAGE. And GraphSAGE does supervised machine learning. It creates embeddings. We'll talk more about how it does that in a bit. And then it's able to have a classifier that says, hey, you've met this threshold. When I see a new event on the network, I can then say whether that's an intrusion or whether it's a benign event. And the fact that in this example, we were doing 600,000 events, and that ends up constructing about 5.4 million relationships. So one of the reasons for using GraphSAGE on Python and particularly on GPUs is we can do all this heavy computational work a lot faster. So as I kind of touched on, KNN, it's fast, it's supervised classifier. It's lazy in that when you run it, each time it recomputes so it doesn't store a model. That makes it very good for what we need it here to construct the graph. And we create these relationships. Rel is similar. GraphSAGE, on the other hand, actually creates a model that you can store, and we persist it inside Snowflake on their Snowpark Container Services. That means that once you've got the model and you've then got live events coming in, you can then do micro batch processing and say, hey, that event there, that looks like an intrusion attempt. So just to kind of summarize all the great work. So, what they found by doing the comparison here and why GraphSAGE and KNN work is you're not relying on the physical links, right? You construct this similarity, which provides a more meaningful representation of the connection events that are most similar to one another. And then you use this to train your GraphSAGE model, and then use that to predict the connection event. So I've got a couple of interactive kind of graphics just to kind of explain how KNN works. So we've got, I'm not on slide 1. So we've got a set of events. Each event has a set of data associated to it. It's a connection event. And the closer connection events are to one another, the more likely they are to behave the same. So be benign or be an intrusion, an attack. So here we can see, because all the ones in red are attack events, this new event is most likely to be an attack event as well. So each event has a set of features, things to do with the network, the protocol, the size of bytes, the amount of time, the duration, and pre-processing requires that you kind of create a Z-score that basically standardizes the numbers, so you don't get large numbers like maybe the number of bytes, imbalancing the model that you're trying to create. And then it essentially does pairwise comparison. It picks out each node in the graph, compares it with others. Obviously, we don't want to compare it with every single node in the graph. That would just take too long. So you have like this kind of 50% comparison check. But that gives you a good enough sense of doing lots of comparisons. And then you find the top 9 that are most similar, and we use cosine. So we're looking at the angle, not the magnitude. So if two connection events are similar, but one went on for a longer period of time, it would have a different magnitude. Well, the duration of the attack probably isn't important. It's more how similar the two events are. That's why cosine is used. And then we have a set of relationships that we create. And this is the important bit for GraphSAGE, right? So we've done this analysis. We've constructed our series of graphs, and then we can then pass this on to GraphSAGE, which relies on the fact that we've got an event. We then want to look at its neighbors, and we look at 9 neighbors and then up to 9 other neighbors. And then whilst we're doing, the GraphSAGE is essentially constructing a vector representation, and it's fine-tuning the weights as it does this comparison. It goes through adjusting the weights to say what things are more important and less, trying to reduce the loss function and feeding that information back. So eventually you end up with a vector that represents the communication event, and that is what GraphSAGE has achieved, is a way of learning how to represent the node as a vector. It's not computing a vector for each instance of the node. That'd be more like node to vec, which you have to run each time. And that's how GraphSAGE is able to store a model within Snowpark Container Services. So yeah, it goes through like a series of training epochs where it's processing the data, adjusting the models, and then at the end, it then stores that model within Snowpark Container Services. So that's kind of how it works. In terms of our product for Snowflake, we have what's called a native application. So you basically deploy it from Snowflake's marketplace. You use SQL. So a departure from traditional Neo4j product where it's Cypher, you have SQL. You use SQL in Snowflake, so it felt obvious to provide a SQL surface that allows you to run our algorithms, and then you can run those algorithms predominantly on CPU, but in the case of GraphSAGE, we support GPUs, which obviously suits the computational complexity. The benefit of running inside of Snowpark Container Services is you're able to run jobs across the compute pool. So, you know, Olga and I quite often, you know, I'm running a set of jobs. I have a node within the compute pool that's allocated to running my job. Then, you know, Olga's running a job. It can fire that job up on another node in the compute pool. So the compute pool scales up and down based on the configuration set in Snowflake. So operationally, you know, we do, you know, billing is based purely on the time that the instance within the pool is running the job. So once the job is finished, you've done your computation and your write back, then we stop the node, and you're no longer paying. Mm-hmm. So as Olga said, we can do this whole thing in 3 SQL calls. I don't want to stand in any way in front of Olga's demo any longer. So we're now going to hand over to Olga's demo. I'll be back at the end to kind of talk about some of the other great use cases that we have for our application that some of our customers are doing and solving. So thanks, and over to you, Olga.
Super, very cool. Thank you very much, Stu, for the intro. Looking forward to the demo. I just wanted to raise one point. If you're watching this live and you have any questions to Olga or Stu, please let us know in chat. We'll have an eye out for your questions. Either we do them in between, or at the end we can collect a couple of questions. So if something is unclear, especially because, you know, we are regularly talking about graphs on this channel, but graph algorithms are not as regular maybe. So if some of these topics or some of these themes are a little bit unfamiliar, don't worry. They are unfamiliar because we don't cover them as much. But if you have questions on it, please let us know. That's why we're here.
Okay. So, do you see my screen?
Yes.
Amazing. So currently I'm sharing my PyCharm IDE. You see the Python Jupyter notebook where I reproduced all the results from our blog post and from the paper. And this Python Jupyter notebook is connected to my Snowflake account. So everything, all the computation about all the SQL queries you will see later, or all the calls to the actual graph algorithms will be computed on my Snowflake account. So you can see here that I have my database connection. This is our account for demo purposes. Here is the snippet of the data I have in the account, and also I've got my Neo4j Graph Analytics application. So yeah, I think we're ready to start. I also have a bunch of code which is placed in other files. In SQL, it's kind of a data preparation because I want to highlight mostly the run of algorithms. So I think we can share this code later, but at this moment of time, let's focus on the actual computation. So first of all, you can see that I have the connection to my database via PyCharm driver. And also, you can establish the connection via the session builder from Snowflake, Snowpark module. So there are many ways how you can connect to Snowflake. So yeah, the outline of my demonstration is that. First of all, we will have a closer look to the actual data. The next step will be we will reproduce the paper or the blog post approach. We will see the final metrics for that. The next step will be a bit of modification of the paper solution or the blog post posted solution when we got some kind of advanced features for the same data. And as the last step, we will introduce the heterogeneous graph for our tabular data. So we will go step by step, and I hope it will be clear for you. So first of all, let's have a closer look to our dataset. The dataset is named like that, and it is sourced from the paper, and the paper has a link to the dataset. So feel free to go there and to download that. But basically, this dataset has a bunch of lines, and every line, like not a bunch, but 600,000 lines, where every line represents the event of connection from some machine to another machine, from one port to another particular port. And it also has the information about the properties of that connection event. For example, the size of information that was transferred from the source to destination or back, the duration in milliseconds, the protocol that was used, and these kind of things. So we can, for example, run this code, and we will see like a snippet of 500 rows here. We see IP addresses, we see some values here, and we also see that this data has labels, and it has kind of more advanced labels for every row. What kind of attack is that? So if you have 0 label, that's a benign. That is a good connection. It's a benign connection. But if you have a 1 as a label, that means it's a bad connection, and it can be DOS or theft or some kind of exploration before the actual attack. And we can get some statistics from this dataset. What kind of attacks we have described in this dataset, and we will see that the amount of good events we have in this table, or good flows. Let's use the term flow for every row. Is just that it is just a little bit more than 2% of the whole data set. That means that this data set has a big shift towards to attack flows rather than the benign flows. Yeah, so we also can have some statistics here. Like you see that I pre-run this Python notebook, but yeah, it can easily be executed now. So first of all, let's go further for our first step. So now we see we have a data set that has over than 500,000 rows. And these rows represent some flow events between 2 machines and 2 ports. And we want to have an opportunity to classify if the flow is good or bad, if it's benign or attack flow. So to do this classification, the researchers in the paper described the way on how to introduce the graph structure for this table. And they used GraphSAGE to do the classification over that constructed graph. So how they did that? So, for example, we have our lines. It is flow 1, flow 2, and so on. We've got the features like protocol type or flow duration or all the other columns we have in our datasets. We've got only the information about the flow properties. We don't use IP addresses on this step because we are trying to classify the flow only based on the features that described in that property columns. So, and to get the graph structure from that information, we are using KNN algorithms. And how does it work in our case? In our case, it compares, like, from that property's features, we construct the vector, and we are trying to find some amount of similar nodes that has this, like, almost the same vector that represents the information about the flow. So yeah, here you see that how like some, I would say, technical information about splitting the data. It is like pure random split of the data set. We have some amount of train ones, some amount of test rows, and we are also do z-score scaling of those features for the, like, we compute the statistics on the train part and apply those scaling features for train and test dataset. In the end, we collect all those computed values into array structure, and that will represent the vector for all the node IDs. And what we have in the end, this is our table that will be used for KNN computation. You see, we have node ID, like some number that represents the row in the data set. And here is the vector with some features that was created from the features we have in our dataset. So here we have, now we are ready to run our KNN algorithm. And KNN algorithm in our application, it is not a classification algorithm. It doesn't do any classification in terms of, it doesn't need any labels, or it doesn't put any labels in the end. It just establishes like the connection between the node based on the similarity. So here you see we've actually, our configuration, the configuration for our KNN call is really rich one. You see only 5 parameters here, but if you go to our documentational page, you'll see that we have a huge amount of parameters. And that flexibility of our KNN implementation allows us to use it to represent exactly the the computational steps that was described in the paper. So because we have this kind of rich configuration here, we can see that we can put a similarity cutoff value in our configuration. We can put the top k values, because like if you take a pure and naive KNN algorithm, it is quite computationally intense. It has n-square complexity, and that means that in our case, if we want like filter out and like that means that we will store only that values that we actually needed. And also here we don't see, but it's a default parameter that KNN by default does some kind of sampling, and in our case it works really well. It significantly decreases the amount of computation, but also if you need to compare everything to get like the most closest nodes, that means that you just need to tackle that particular parameter. I see that because we have this half of our presentation, like the introduction part in our presentation, my compute pool is a bit staled, and that's why it takes almost 3 minutes to run this application, because Snowflake had to find the actual machine for me to spawn the compute pool and do all the computation. But actually you can see here that the actual run of the algorithm, except all that all that work that was done by Snowflake, the actual computational time for our algorithm here is just 35 seconds. So here is some logs. You can get some log from the run, and in the end, we can see that so we provided the table with nodes, and in the end, we've got as the result the table with relationships. And we can see here that the amount of relationships is 5.4 million relationships. That's almost like when you got 600,000 nodes, and every node has 9 neighbors. You will have 5 plus million relationships in the end. So this is how it typically looks like when you visualize this graph. It's just like a small subset. So every node will have up to 9 neighbors, and some of nodes can be neighbors. Also, you won't have all the isolated nodes. No, like some of these snowflakes will be merged. So it's a good news. Now we have a graph for our tabular data, and that's why we can run the GraphSAGE for that. So I think let me start it. Maybe we can in the end see it. Okay, so for the GraphSAGE, we have to use not we have to kind of provide the information. Like GraphSAGE has two steps: the train step and the prediction step. And train step requires label information. So we have a row, we have a flow. For the flow, we have a vector that represents some features for that flow action, and we have a label 0 or 1 that shows us if it's benign or the bad connection, the bad flow. So here for the trained data set, we have our label as integer, and for our test data set, we put null as a label. So that's why our GraphSAGE won't have any information about, like we kind of hide part of the data set from GraphSAGE to actually measure the metrics in the end. So this is the snippet from the data set. So you see we have a vector for every node ID, and for some labels, we have null values, which are shown here as a none. But it's a kind of just like conversion issue from the PyCharm notebooks things. So we're also having the result of our KNN run. We have a table that represents the connection. So we've got source node ID, target node ID, and the actual score. The score represents how close those. Oh, I think that's because that was pre-run before. Okay, let's drop the previous model. Yeah, so now let's rerun. So, and that graph, we pass this information. We've got information about our nodes with vectors, and we have this. This is the table from the KNN step. And we've got a bunch of compute parameters we have to provide for GraphSAGE. And you also can see that here we use GPU compute pool. Our GraphSAGE implementation can work on GPUs too. So if it works better for you, please feel free to use GPU compute pool. You're also allowed to use all the other compute pools we support. For example, CPU compute pool. We have 6 or 8 of them, like small, medium, large, high memory, and like. So the various kind of compute pools. So the current call will be executed on the compute pool with GPUs, and we've got a bunch of compute parameters here. We provide the model name. We provide some other parameters. Here you can see we provide num samples. That means that our GraphSAGE will gather the information from the 9 random. For our case, it's all the neighbors of the the maximum number of possible neighbors for the node on the first round of neighbors, and up to 9 neighbors for the second neighbors. So we also provide some information about split. We provide some information about desired batch size. Typically, it takes, I would say, 4 minutes, but again, some amount of this time is spent by Snowflake by getting the compute pool for you, getting it ready, and uploading the image with our implementation. So the actual run is much more quicker. So I think we can come back later and see the actual time for this run. But
maybe what we can do, because you picked GPU as a compute pool, maybe you can. Is there a reason why you picked it? Is this a recommendation?
No,
or
no.
Do you think, is there an advantage of the GPU versus the CPU, or is it is there preference?
When you are using the small machines, it's better to use GPUs one. We support only S size for the GPUs. We don't support any big GPUs in our compute pool, but if you need, I think you can contact us. We can consider it and maybe introduce it at some point. But at this point of time, the maximum compute instance family for GPUs is S1. So if you have the graph that won't fit into this instance size, you can use the larger CPUs one. So yeah, the recommendation is start from GPUs, but you are not limited by just using GPUs for GraphSAGE training. Okay, so yeah, once you've got your model, you can use it for prediction step. And for prediction step, we will see that for all the nodes that had null as a label in our dataset, it will provide the output label. And based on that information, we can compute. Here is the snippet of the prediction from GraphSAGE. You can see that we have some node IDs, we have predicted class, and we also have predicted probabilities. You will see later that like we predict class like from these predicted probabilities in a very simple way. To get this predicted class, we just use 0.5 value, and if it's larger than that, we use like one class, and if it's lower, that's like we use 0.1 class. And you will see that we will kind of tackle this parameter later to get the better metrics in the end. So I think I have to be a bit faster. Yeah, now we see that that's the training has finished. You see that the actual time of training was about a minute. Let's have a closer look. Yeah, let's see. This is you see that it was 1 minute 17 seconds, but we see that our cell ran up almost 5 minutes. This is because of Snowflake need to get the machine for you and need to run like all this required actions to get the machine for you. So here we estimate, like here we got from our tables with prediction, we are computing the confusion matrix, and based on that confusion matrix, we can get the metrics values. And those metrics values are really close to that reported in the paper, and that was really good. But at the same time, you can see that our data is really unbalanced. And for unbalanced data, it's worth to look at macro, look closer to macro F1 score. That means that you really pay attention on proper classification within every class. And for example, for if you it is some example on giving you some understanding what's the difference. Because for example, if you have 1,000 flows and only 23 of them is benign, and you get the very dumb prediction of that everything is bad flow. For this case, you will get F1, like in this case, you've got micro F1 score. Your micro F1 score will be really high. Your weighted F1 score will be also really high. And only macro F1 score will show you that something requires your attention. So in our case, for macro F1, we see here that we have 0.8, which is not bad. But we also see that we've got a bunch of false positive values, and this is something that we can work on. So I also would like to show you how to visualize this graph. You can have a visualization for your graph. Of course, you won't need to visualize all the more than 500,000 nodes, because you will see only like all the nodes, and that won't help you. But you can get some kind of sampling from your data. This is just I've got just 50 nodes from our node table. I've got the corresponding relationships for that. I do some SQL queries here, and I'm using Neo4j Viz module to visualize our data. We've got from Snowflake call, and you provide like the information about the tables with your data and the tables with your relationship, and soon you will have like almost instantly you will have a visualization. So here you can see that you can explore your data. You can see that our data is the kind of our sampled data is a kind of snowflakes here. Probably it's better to be colored in blue, but okay, it's yellow. It's summer, small sounds. Okay.
Sunflowers.
Yeah. So you can see the sample of the graph. It's really nice to have this kind of visualization. So I think I will move a bit faster because we have a limited time. But let me introduce you to the next step of my demo. Is like the kind of improved or advanced feature engineering for our data. First of all, we've got bytes and bytes information about amount of information that was transferred from one node to another node, and sometimes it's 0 and sometimes it's 100,000s of bytes, and that means that it's a very wide range, and that's why we can use logarithm function to kind of narrow it to have not so wide range of the values. Also, TCP flags protocol and L7 proto also can be one hot encoded, and that's why our datasets become like our vectors become to be 26 dimensional instead of 8 dimensional. So we have kind of a bit of a richer representation, and for example, for protocol there are only 3 numbers like 6, 6, 7, and 17, and that doesn't mean anything that 6 and 7 are really close to each other. Yeah, so and 17 is quite far. No, it doesn't mean anything. That's why it's worth to be hot encoded. We're also using cross-weights.
Sorry, Olga.
Yeah.
We had a couple of questions, and I don't want to interrupt you really, but I think it's probably a good idea to do those before we jump into the chapter 2 here. One comes from AJ. AJ asks, and then maybe you show this later, so let me know. But he says, how do you pass the trained GraphSAGE embeddings and predicted labels back into the Snowflake tables? Is that something you show, or how do we?
It's a very good question. Thanks for that. We have 2 kind of flavors of a GraphSAGE in our application. One is the first one is the classical unsupervised one, which produce the embeddings, and the second flavor is the GraphSAGE for node classification. That's why I used this. This option for us is GraphSAGE node classification predict and GraphSAGE node classification train. It creates the special model for classification. It does all the magic about embeddings, and it has the different loss function. It has a bit different approach, but yeah, if you need embeddings from the GraphSAGE, you need to use GraphSAGE unsupervised train and prediction combination.
Cool. And then there's one more question from Jibo. Jibo asks if you understood the process correctly. So he says, or she says, the process is to make the flows, so connections between machines, nodes with features, representations as vector, and then to have them as a table, and then the table feeds the KNN, and Snowflake then works with these tables.
Yes, Snowflake, you're right. We've got table. We construct feature vector from some columns of that table, and we run KNN algorithm. KNN algorithm returns us the table that represents similarity between some nodes, and we treat this result as the relationship table. And a relationship table represent like, maybe I had to put more attention on that, but I think let me show you. Yeah, here is the node table. Here's the relationship table for GraphSAGE. Node table has just like, it's a must to have a node ID column for node ID for node table, and relationship table kind of, it can be treated as an edge list. Yeah, that's kind of that this relationship table represents the connection between those node IDs from the correspond node table. So that's why we've got just node table. We've got node table from initial raw data. From that node table, with the help of KNN, we've got relationship table, and having this node table and relationship table, that two tables defines the graph, and that graph can be used for GraphSAGE to train the model to do the classification at the end.
Okay, cool.
Okay, cool.
And just one more point, the notebook and the presentations Olga and Stu share with you today, we will share them with you afterwards. We will try to make it available and put it in the video description, so you can play with that.
We can share it. So here this is some about like, let's go back to the step 2 when we've got some improvements for our case, and we are also using class weights. We are also using class weights parameter for GraphSAGE, and we also will tune the decision threshold, which I mentioned before. So here it is pretty the same, but now our features are quite longer and more granulated. And also here we see that and also for the step 2, I prepared the different split, but I won't put much attention for that now. It's nothing special. It's just like having the awareness that we don't use duplicated lines in train and test datasets. It's a bit more correct approach for splitting the datasets. Again, we can run KNN. The rest is pretty the same. We run KNN algorithm. We've got the different table with relationships. We've got GraphSAGE node classification trained for that. We use class weights true because we have an unbalanced data. Here we've got a prediction here, and in the end we are also having a procedure of kind of tuning of the threshold, where we decide if the value of predicted probability can be treated as benign or the bad flow. So here is some code, and here you see that for the tuned threshold, we've got much better macro F1 score, and it was 0.8 on the previous time, and now it's 0.84, which is good. We've got less false positive and false negative value, which is really nice. Cool. And the next approach is to actually get the information. Like the last advanced step is introducing the heterogeneous graph. What if we have not only the flow, we will call it pattern here, like, because pattern is a good term for that, because it represents some particular properties of the connection act, and some other metrics for that. But also we can get the information that this connection pattern happened between two particular hosts, and it is and we call it an event. And we're also introduced the node type IP, which like in our case will add some information about that that some particular flows happened with some different, for example, IP addresses with some different hosts. So here we got a bit more complex procedure. Again, we've got 26 features as we had on the version 2, on the step 2. And we've got an event when we add information about source and destination of that flow or pattern. And we're also having nodes IPs, and we can it is kind of naturally we can get these relationships naturally from the raw data, because every row has a pattern. It's a subset of the row. An event is kind of our pattern plus information about source and destination, and the IP addresses is also, when we get just the information about the IP addresses, we see that several events happened or related to some particular IP address. So here we, in the same way, we can have a look only on these kind of nodes, only patterns, as we did for the previous 2 steps. And we run KNN algorithm for that. And I think it's better for me to show you the visualization. So you see here that we have our patterns of flows, like it's our Snowflake instance we had previously. And now we see that we have IP addresses nodes and event nodes that kind of connect those flows between each other. And when you do, and our target now is to classify this event. Was it attack, or was it a benign flow? So this is our target now. And because our GraphSAGE can get information from the neighbors, that means for this, that the second neighbors will, for example, if for GraphSAGE, it will get information from this event too. It is something new in the flow, and that will help us a lot. So now let's go back to our. So as I mentioned before, we've got. Do we have a bit more time, or should I stop here?
We can spend a couple more minutes.
Okay. So I will be really fast. So we have the same KNN approach as we had for the previous step, just for patterns. But now you can see that we use the really heterogeneous graph for the GraphSAGE. We see that we have event nodes, pattern nodes, and IP nodes, and we have tables that represent the connections between patterns, between events, and patterns between events and IP addresses, and the way back from events and IP, because we kind of separate inbound connections with outbound connections. So the parameters are pretty the same. We've got like a minute and a half for this run, and we do the prediction for, again, for the prediction, we have the same graph. We put all the information for the prediction, but we really need to have an answer for our event nodes. Is the event is good or bad? And here is some evaluation. You can check it later with the source code provided. I think we will share this Python notebook. You can see that for our current for these data sets, there is some events that sometimes works as good hosts or good events, and sometimes they're like kind of infected and works as bad flows, and that's why we cannot get like any kind of any close to 100% accuracy, but we could reach the theoretical estimation for this data set. So we have Oracle in terms of if we get the real answer, if we get the real answers from the data set and compare it with our version 3 value, we will see that we've got pretty good macro F1 score. We've got almost the same amount of false negative and false positive values. So this heterogeneous approach with introducing the information about the hosts and the IP addresses is really helpful and powerful. And again, this is pretty the same code I had for the visualization on the step number 1. And because it has several tables that represent relationships between different types of nodes, we've got this really nice visualization in the end, which will help you evaluate if it's something you expect from your data or not. So yeah, that's all for my demo. If you have questions, please.
Cool. Thank you very much, Olga. In the interest of time, I think we'll need to wrap it up a little bit. But in essence, can you confirm that, if I understood this correctly, so you added a little bit more context with the events and with the IP addresses around the initial flows, and that helps obviously validate attack paths or validate if something is benign or malicious.
Yes.
Makes it a little bit easier to judge.
Yes,
basically.
that's true. By introducing the information, like we are not introducing the information about IPs and ports as a features. We introduce it as the structural information. We are not like using the actual values of IP addresses. The only information we need is just that 2 events or several events are coming from or coming into one particular host. So the value of IP addresses is not really matter, but it's really a powerful thing to utilize this information as a graph in the end, and get everything you can get for this data set as the metrics in the end.
Yeah. Cool. Amazing. Thank you very much, Olga. Thank you very much, Stu. Do you have any last words for today?
No, thanks. I was going to run through a couple of other sort of examples, but as we're out of time, there's a couple of slides in the slide deck, and we'll make that available. People can have a read through. Again, thanks, Alexander, for hosting us today. It's been great to chat about this work, and yeah, thanks for all the great questions out there.
Yeah, absolutely. Thank you for joining. Thank you for spending the time with us today, and also spending the time writing the blog and the analysis. I hope this was interesting to you. Like we said, we'll share the notebook and the blog as well as the slides in the YouTube video description. So if you wanna play it with it yourself, check it out. We'll make that available within the next few days. I wanted to invite you to the next Neo4j live stream that's already happening next week, where Pavan joins me and talking about building automotive parts intelligence using graph memory for supply chain resilience. So he's using a hybrid approach with graphs and vectors to analyze impact analysis on supply chain. So this is another network that's been impacted. So in this case, I think we stay true with the theme, but a different approach. So it should be interesting as well for this approach. So join us next week. And I'd like to close with a reminder of notes. It's going to happen in November. The call for paper has ended, but we're currently working on the agenda. Road to Notes will be running again in October for interesting workshops. I'm currently collecting the topics for that, so that should be fun and interesting. If you are interested, you can already register for the event and be updated when anything happens. And yes.
Alexander, I've just sent you a link in the chat. If you could post that one as well out to everyone.
Yes.
We're starting a virtual user group for Snowflake. So people who install our app will be able to register for the virtual user group. We're hoping to have the first session in September. The registration form asks you sort of questions about what sort of content you'd like to see. We also want to see people contribute from their own projects, and it's not all about. It's being hosted by DevRel. So yeah, thanks.
Yeah, that's great. That's great. So yeah, join that, and let's always interesting to hear your feedback, hear what you build. If you play with this or anything else, it's always nice to hear what you do. So let us know. Yeah, I think that's it for today. Thank you very much for watching. Thank you for joining. As Stu said, thank you for your questions, and again, thank you Olga and Stu for the great presentation today.
Thank you very much.
Thanks.
Thank you.